Okay, hi, my name is Philip. I'm from the University of Innsbruck. I'm presenting AutoDAG here at WoSX today. And AutoDAG is an end-to-end automated platform for the creation and optimization of serverless DAGs in federated clouds. But before I show you the architecture, let me quickly show you the problem we are dealing with. So we want to deploy a monolith to a serverless environment. The monolith here is represented as these three statements. And the first thing to do would be to specify the monolith. And this would mean that for each statement, each task, we would need to assign to a serverless function, or in a more general case, to a worker. In the most naive placement would be to place each task into one function, but there may be better configurations. Like here, if statement 1 and 2 exchange a lot of data to improve data locality, we can place them on the same function and keep statement 3 separate. The next step would be to assign each function the correct resources, meaning that statement 2 might be a little bit more demanding, so we would need to assign it more memory, but the other two can stay at the minimum memory requirement. After that, we can profile the application to recognize opportunities for parallelism. Imagine that statement 2 in fact iterates over some input files and for each file does some processing. And with profiling, we can easily uncover this data parallelism and execute an instance of statement 2, each with one file only, but in parallel. And lastly, what we have to do is to derive explicit and implicit dependency. Imagine how you would move a monolith to a serverless environment. It would be that each function gets connected to some shared storage, where each function has access basically to all files, because we don't know at the beginning of what files each statement is going to use. In fast, this would even mean downloading the whole directory to the function, because right from the statement we cannot infer anything. That's why here in the second example, or how to make it better, is to profile the application. Like we receive some statement and the statement operates on a directory, to track each file access and then to optimize the data transfers. And this works now even for some cases where we have irregular data dependency, where a successor may even wait on the data of two predecessors without or just given the monolithic code with a directory, we cannot see this. We need to profile this before, and then we can reduce the data transfer just to the needed ones. And to achieve this, this is the architecture. So we propose this threefold or this three pieces architecture. We have a falsifier which converts the monolithic code into a serverless DAG, a profiler which profiles the file management and data flows, and lastly a scheduler which assigns each task its the best resources. The main innovation here is that these steps are interdependent, so we cannot create an optimal DAG without scheduling. We cannot schedule without profiling, and we cannot profile without first deploying the graph. So we address this step or this whole process end to end and achieve probably or better solutions than the state of the art. We tested PWA and montage workflows on AWS and GCP. This is the DAG AutoDAG created. So naively, montage would have 12 functions. Here we only have, or AutoDAG merged them to 7 functions to reduce data transfers. However, these two are kept separate because one of them is computationally very slim, the other one computationally very demanding. So it makes sense to keep them separate and assigning them different memory. And the GCP DAG has one more function because GCP has a higher intra-region bandwidth. We are also faster and cheaper than the related work. So we are not as fast as let's say, this works which use sky computing, so they use more regions, but we are also not that cheap as like M2 fast and what is this, Node 2 fast, because they do not use parallelism at all. However, they are also way slower than we are. So from all the solutions which use parallelism, we are faster and cheaper by running in one region only. Okay, that was all. Thank you for your attention. I'll be happy to answer a question. Sorry for being slightly over time.
No problem. Thank you. If there is one question, please go ahead. If not, we can go to the next presenter. There will be also time at the end of the session for questions if you have. Okay, so let's go to the next talk. Philipp, please stop sharing your screen. Okay, thank you. Okay. Let me know if you cannot hear the audio, but otherwise I will just start now.
Hi everyone, I'm Matthijs Jansen from the VU Amsterdam, and I'm here to present my work done together with IBM. The topic of my talk will be about machine learning as a service. The idea of machine learning as a service is that if a user has a job, for example, to fine-tune a machine learning model, they can define this job, submit it, and the job eventually arrives at the scheduler. The scheduler will fill in any missing configuration parameters that the user didn't define and deploy the job on a GPU cluster. Now, where this research project began is with the vision that we would like to have users define as little parameters as possible. So they would only have to worry, for example, about the machine learning model they want to use and what data, and they don't have to concern themselves with all the other parameters. Now, why is this an important research topic? That is because configuration parameters majorly impact performance. For example, in this graph, vertically, we can see the performance of a job, a machine learning job, with a couple of different configuration parameters, where a higher score is better performance. So just for these four performance parameters, we can see a difference of more than 10x between the worst and best performing configuration. Moreover, we can see that there is no clear trend for any parameter in performance. There's no one best setting anywhere. So as a result, if we look at machine learning as a service where we don't have 4 parameters, but many more, with 10,000s or 100,000s of unique parameter combinations, the problem now is that if we look at the state of the practice, it mostly relies on default parameters. So if a user doesn't assign a parameter value, we use a default. But the performance of configuration parameters is so complex and difficult to predict that a single default value will always give you subpar performance. And the state of the art primarily ignores configuration data. It focuses on making great schedulers, but not on the data that these schedulers need to base their decisions on, which is what we will look at. So we have 2 major contributions. 1, creating configuration data, and 2, evaluating the impact of various amounts of configuration data on scheduling for machine learning as a service. So how to create configuration data? We find 7 configuration parameters, and within this configuration space of 72,000 unique combinations, we benchmark 5,000 combinations, and we get execution data of those. Then we use multivariate regression to predict whether the missing configurations, where we don't have data from, whether they are valid using GPU memory as a proxy, and what their performance would be. Now, the result of our regression is a 4.2% error for validity, so for predicting GPU memory, and 9.4% for predicting performance, which is quite small, given that the range between the worst and best parameter is about 4,000% within our configuration space. So 9.4 is relatively small. So we also look at how many data points we would need to make accurate predictions. And we can see that already at 600 points, data points, we have a prediction error of just 11%, meaning you don't need thousands and thousands of actual benchmarks. Now, given these predictions, we build a configuration database that houses for each configuration parameter combination, whether it is valid and what its performance is according to our predictions. And we expose this along with various other configuration sources to schedulers. So we can measure the impact of various configuration knowledges on scheduling performance. So what we see in our evaluation at the bottom, we look at two algorithms, FIFO, which is a state-of-the practice scheduler, primarily using data from users, so users defining all parameter values. And we can see if we expose it to our configuration database, a 78% reduction in job completion time. And even for a state-of-the-art scheduler like SIA, we see a 70% reduction in job completion time, showing that we can greatly increase the performance of schedulers if we expose them to better configuration data.
Hi, I'm Mohammad Reza Malik Abbasi, Reza for short, and I'm from Scalable Software Systems at...
Okay, I think we can go to the next presenter. Daniel, you will also have some time at the end of your talk for demo, right? You have reserved time, so go ahead. 5 minutes for talk and then demo.
You see my screen?
I see your screen right now, PyRun.
Vale. Okay. Hi everyone, I'm Daniel Alejandro Tejeda from Universitat Rovira i Virgili, and today I'm going to talk about PyRun, a platform designed for effortless, serverless, and distributed Python on your own cloud. We all know that Python is fantastic for data science, AI, and general computing. In this case, frameworks like Lithops for serverless functions and DAGs for distributed computing offers an immense power, but let's be honest, setting them up, managing runtimes, and monitoring jobs in the cloud can be a problem, so, pulling you away from your actual coding and research. So that is where PyRun comes in. It's an integrated cloud Python platform that simplifies all of this entire process. Imagine a VS Code like web interface where you can manage your code, file, and even use a terminal. With PyRun, you have an automated runtime management. Just define your Python dependencies in an environment or a Docker file, and then PyRun will automatically build and deploy that environment. Also, it offers seamless first-class support for Lithops, function as a service, DAS, Ray, Kubet, among others, all running securely on your own Amazon account with the support to multiple backends like Lambda, VMs, Code Engine from IBM. In addition, you will get detailed real-time monitoring to understand exactly who your jobs are performing. So the objective of PyRun at the end is to let you focus on your code while PyRun automates the rest. Here, we will look an example with serverless, especially using Lithops. With PyRun, automating all the configuration, like choosing your Amazon Lambda backend, setting memory, or other parameters, all of that is done through a simple UI. No more fighting with complex JSON configurations or something like that. You just write your Python functions, and then PyRun handles the serverless orchestration. In our benchmarks, like generating Kerchunk references, satellite data using 24 parallel functions, PyRun was up to almost 15 times cheaper and 5.4 times faster compared to alternatives like Coll when using a similar fast workloads. So this means into a faster results and significant cost saving from your serverless task. And as I mentioned, PyRun is not just about fast. It brings the same simplicity to task. We have seen just cluster creation times up to 2.5 times faster for workloads like generating IPCC climate plots. And a part of from being fast, cheap, and simple, PyRun also offers a collection of ready-to-run pipelines with complex real-time, real-world examples from geospatial to metabolomics. And also, from these pipelines, PyRun offers AI and machine learning features. We have pipelines for audio recognition, image recognition, distributed machine learning with DAGs ML, and even running large language models with Ollama, all with the advantage of the easy environment management for complex AI libraries. So this is too short, sorry. We have more time to the demo. So if you are looking to experience effortless cloud Python, I encourage you to try PyRun. You can get started at pyrun.cloud and find more details in our documentation. The key takeaways are faster time to results, that is too important, reduce cloud complexity and the operational cost, all with an integrated and versatile platform that we will see after. So PyRun empowers you to leverage the full power of your cloud account without getting bogged down in the setup. I think it's a fantastic product. So thank you for your time. If you have any question.
Go ahead if you have a question, and remember to unmute yourself. If not, Daniel, you also wanted to run a demo, right?
Yeah. I can start a demo if you want.
Go ahead.
Okay, so this is PyRun. When you enter to PyRun, you will see this web page that will allow you to interact with the serverless management and all of these things that I said before. At the start, you will find a window to log in or create a new account. So in this case, I have already an account created. As an example, when you create a new account, you will see something like that. PyRun tells us that to start using it, we need to link our Amazon account to PyRun. So to do this, we will click this button here. And it will redirect to our cloud account section of our user. And then with just one click here, we will connect our Amazon account to PyRun. As I said before, the objective of PyRun is simplicity. They do all the things with just 2 clicks, 1 clicks, anything. So in this case, we will accept the condition and create a stack. This will connect our Amazon account to PyRun. So the platform will begin executing a series of process to create and automate all the necessary resources in our Amazon account. So you don't have to take care about anything. In this case, when you have your account connected, we will see something like that. In this case, we can see different sections in our account. We have the home section that I saw before with tips and more, and we have the pipeline section. This here we can find a real-world examples ready to be executed with just 1 click. If we want to run, for example, an image classification, just tell the instance type, put a name, and then it will start running on your own Amazon account, all with simple clicks. We have examples with Qubit, image classification, water consumptions, among others, a lot of examples. So we also have other sections like the workspaces or monitoring. Workspaces, we will tell about it later. Here on the monitoring section, we have the monitoring of our last tasks. Here we can see information about the time of the task to be run, CPU, disk, memory, usage, all of these, and then we will go to the workspaces section of our user. In this section, this is where we will manage all of sessions and workspaces. So in this section, we have two options: the option to create a workspace to start developing from scratch, or just select one of the pipelines that I mentioned before. In this case, we will create a new one. We have the option to choose the VM that will run all of our workspace with the files and all of these things. We have two options to start coding with lithops or DAGs. It will be more options in the future. And then we will put a name, test or something like that. And then we click on run. Here, we will create, it will start another automated and simple and transparent from the user that create an environment that will allow us to develop our code or launch our code in a cloud with simplicity and fast and cheaper way than our competitors. So in this case, we have another pipeline already running, the fast with a simple lithops code. We open it and we will find a VS Code interface that already integrate and configure the beginning of developing. Imagine that we want to run this code, for example. We will simply click on the run button here, and then it will start our coding with just one click. This is the same that I said. All this talk is just one click, and then you will have your code running on Amazon, on IBM, or something like that. So as I mentioned before, PyRun, the PyRun goals is to be simple and integrated. So we see here two files, the example, this code, this lithops code, and also an environment file. In this file, we will put our dependencies or package that we want to install on our workspace and the image that our workers will run on the cloud. Another feature that I think that is interesting is the possibility to change between different backends without changing any line of code. So here, if we see the log, we will see that this execution is running on Amazon Lambda. But if we go to the UI and then change the backend with just two clicks, it's so simple. Then the next execution of the code will be running on CodeEngine without changing anything, without doing a rebuild of our runtime, without anything. So the I think that the platform is a good option to people, to data science that doesn't want to put their time managing resources on the cloud. This is PyRun. PyRun do all of that work automatically and let the user to code and put their time on developing. So this is all. Thank you for the time. If you have any question or anything, I will try to answer it.
Yes, thank you, Daniel. If you want to ask the question, just remember to unmute yourself first. And I actually have a quick question. Was not clear to me, if you have a group of users that want to use it, do you require each user on their own to get like AWS account and IBM account, or could they share, the same account?
Now they must have a separated Amazon account, but we are working on that, and in the future, in 2 weeks or something like that, we will allow to multiple users working on the same Amazon account. So I think that it's a good question.
Are there any other questions? Also, remember, if you have any questions about the first talk, about second talk, the author is not here, so you can ask a question, but I don't think anybody answers it. And if go ahead if there are any questions. If not, we have 5 minutes. Well, let's make it maybe 8 minutes break. And